All right, so now we're going to move on to lesson 2.1, which is actually the first lesson of trigonometry, and it's introducing angles in standard position. Now, when we talk about angles in standard position, there's a couple things to highlight right away, or a couple things to note importantly here. First of all, we're going to have this terminology pop up called, which is the initial arm and then the terminal arm. So it's really important to highlight those two pieces and realize that when we talk about these two things, our initial arm is always going to start on the positive x-axis, and then our terminal arm is, like it says in its actual vocabulary, it's going to terminate or be terminal in one sort of quadrant here. So when we look at this piece here, again, the initial arm will always start in our positive x-axis or on the positive x-axis, and the terminal arm can either rotate counterclockwise or clockwise to make either positive angles or negative angles, depending on what type of solutions we want to be looking for. Now, again, I would just make sure you highlight that row here or highlight this piece that says exactly that piece here. And what I'll do is just tidy this up just a tad so that we have our terminal arm highlighted there. Now, when working with angles and triangles, obviously we know they have to be less than 180, or else we have something when it's greater, that's not going to make a triangle. In fact, we know that the inner angles of any sort of triangle sum to make 180, hence the triangle sum theory, which says that all interior angles of a triangle add to 180. And if that's not the case, then we don't have a triangle in that situation. Now, let's complete an investigation in angles in standard position and just talk about group A versus group B, a couple different examples in which we show how an initial arm and a terminal arm can be used on the Cartesian plane. Now, in group A, we see that all of these points are going to center at the origin. So it's really important to look at this and be like, okay, 0, 0, 0, 0, 0, 0. Any angle in standard position, the initial arm and the terminal arm always are centered at the origin. Very, very important here. When we look at group B, you see that that's not the case. Some of them have an origin point, or a vertex point, I should say, a vertex, not an origin, but a vertex point that is off of the origin. And then some of them are on the origin. Some of them, again, are shifted to the left of the origin and make their vertex somewhere on the negative x-axis. We don't want this. So in fact, when we talk about angles in standard position, the two big characteristics we want are the following. The first characteristic, we want the initial arm on the positive x-axis. So I'll say initial arm on the positive x-axis. Awesome. Now, that's our major piece there. So we want to make sure that that's taken care of. In terms of number two, we always want to have the vertex on the origin. So we're going to say vertex on the origin. And if we have those two pieces here, then we are satisfied. And we consider this to be good because these would represent angles in standard position. The part B, or the group B, they clearly don't have that. So we want to look at this and be like, nope, that is not going to be good for us there. All right, awesome. Let's scroll down here and just again introduce some terminology, or introduce the kind of, I guess if you want to say, the characteristics of angles in standard position. When we consider angles in standard position, what we want to do is, again, we want to make sure that it is on the origin, or that it is centered at the origin, its vertex. So we have an initial arm and a terminal arm that are both starting at the origin and then work their way out. The initial arm lies along the positive x-axis, another very, very strong point that we want to make sure we highlight. If we rotate counterclockwise, this is considered to be a positive angle. So as we start rotating counterclockwise, whether it be in quadrant 1, 2, 3, or 4, we're going to consider this all to be positive. If we rotate counterclockwise, then we're going to consider this to be negatives. And associate that with the diagrams below. It might be a good idea just to consult with those diagrams here, where we say, hey, you know what? We're always going to start on this positive x-axis, whether it's a negative or positive angle, but then just depending on which way we rotate, this will be our positives. And then if we rotate down to start from the x-axis, this will be our negatives, not our positives, but this will be our negatives. All right, now let's go to our next page here, where we're going to sketch out some of these angles, whether they be positive or negative, and then see which quadrant they lie in and what their initial arm and terminal arm look like. Okay. So if we want to get to 120, well, first and foremost, we always have to draw the one arm on the x-axis. So we're going to do that here. We're going to look at this and be like, here's my initial arm. And then if I go to 120, well, we know that if we're in the first quadrant, all of this is between 0 and 90. This is all between 90 and 180. So clearly it has to be somewhere here. And in fact, it's probably closer to the 90 than it is the 180, but it's about central between those. So we could draw it roughly about like this. Perfect. Okay. Now, what I'm going to do is I'm going to sketch over top of this. I'm just going to have my inner piece here indicating that we've rotated counterclockwise. I'm going to indicate that this is 120 like this. And then when we look at this, if we talked about it in terms of the quadrant, because they said sketch each angle in standard position, well, that's the sketch of the angle. But now what we want to do is make sure that we state which quadrant it lies in. In this situation, this is quadrant 2. So I'm going to look at this and be like, therefore, quad 2. Perfect. And if you wanted to, you could write out the full quadrant, but just for the note's sake, I'm just going to truncate it as quadrant 2. Okay, let's do 220 now. Now, if I look at this one, I'm going to draw, of course, right on the positive x-axis, my initial arm. You always want to make sure it's there. In terms of where 220 lies, well, if this is 90, this is 180, this is 270, it means that it's somewhere in quadrant 3, so it's going to look something like this. We're then going to write over that we started on the positive x-axis, we rotated around like so. This ended up giving us that this was an angle of 220, and what quadrant does this lie in? Well, this is quadrant 3. So if we go counterclockwise around the circle, we start in quadrant 1 and then go 1, 2, 3, and 4. So this is in quad 3. And it's really important that you're using Roman numerals because that is pretty standard with this, including when you go to like Math 30 or anywhere beyond. When we talk about this like manipulation within the Cartesian plane, we always typically use Roman numerals representing these numbers here. All right, let's go to negative 320. Interesting. Okay, so whether it be a negative or positive angle, what we're going to do is we're going to make sure that we put our initial arm on the positive x-axis no matter what. Then what we're going to do is we're going to rotate around and think about it this way. If this is negative 90 when we go this way, this is negative 180, this is negative 270, that means that it's going to lie somewhere over here. And so what we're going to do is we're going to write an arrow like this in quadrant 1. We're going to write our arrow going around the circle counterclockwise, or sorry, in the clockwise direction, not counterclockwise. Counterclockwise is the positive. If we go clockwise, this is considered to be a negative angle. We're going to make sure we write this is negative 320 degrees. And then when we write our reflection, we know that this is quadrant 1. So quadrant 1 doesn't just sporadically change from here to down here because we rotate this way. We're going to consider this still to be quadrant 1, the top right quadrant. And therefore, we're going to say that this is located in, or it terminates in quadrant 1. Awesome. Okay. Now, the most important thing of this lesson is to highlight this line here, talking about the definition of a reference angle and what this means. A reference angle is the angle that is between the terminal arm and the closest x-axis. So important that you highlight that. If you don't highlight that and you just move past this, you're going to be stumped for when you go to the 30 level, and then potentially when you deal with anything more in this unit. We want to make sure that when we talk about a reference angle, it's always between terminal arm and the closest possible x-axis. Now, the reference angle is always positive and it's between 0 and 90. So even if we rotate in the negative direction, we're always going to refer to it as a positive angle no matter what. And so let's make sure we highlight that subpoint here where the reference angle is always positive and between 0 and 90, aka an acute angle. Now, let's use some angles in standard position to then determine the reference angle based on the idea that it's between the terminal arm and the closest x-axis. So I'm going to go down below here, and again, when we have an angle in standard position, we always start on the positive x-axis, we rotate around. In this case, 150 is in quadrant 2. We're going to then label this here and be like, okay, here's my rotation, here's my 150. And if I end up wanting to get this angle for the reference, well, the reference angle is between our terminal arm and the closest x-axis, meaning this is the angle we're looking for. So let's indicate that here. This is going to be our theta r, or our reference angle. And in order to get that, we know that this endpoint here is 180, or that's technically 180 degrees, because if we started over here, this is 0. We rotate it left or counterclockwise, which puts us to 180. And so to get the reference angle, I'm just going to essentially go, well, what's 180? And maybe I should write it first as theta r. Theta r is equal to 180 minus the 150. This is going to end up giving us a reference angle of 30 degrees. There's your solution. So we're going to make sure we highlight that. Perfect. All right. And maybe I'll just highlight the whole row just to indicate that here's our calculation, here's the actual value. Okay, let's do the same thing for 230. So when we look at this one here, we're going to start on our positive x-axis just like we always do. 230 is going to put us into quadrant 3. And now what we're going to do is we're going to rotate around as such. This is going to end up giving us 230 degrees when we rotate it. Our theta r is always between the terminal arm and the x-axis, so it's going to be located right in this little pocket. In order to solve for this, we're going to say that our theta r, or our reference angle, is equal to, well, we have this degree of 230 degrees, which is the full rotation. We want to subtract away 180, which will give us that little sandwich piece between the x-axis and the blue terminal arm. So we're going to subtract 180, and then this is going to end up giving us that the theta r, or the reference angle, is 50 degrees for this solution here. All right, let's go down here. We go to negative 125. Negative 125, well, first and foremost, we always start on the positive x-axis, so I'm going to write it here. We know that if I rotate negative 125, it puts me over into this quadrant, and showing this very clearly, I'm just going to make sure I rotate in this situation clockwise by negative 125 degrees. Therefore, our theta r is always between the blue line, or our terminal arm, and the x-axis that's closest. What we want to do to calculate this is we're going to calculate it using positive values. If this was 0 and this is negative 180, then in order to calculate this, we could actually just theoretically use positive values. I'm going to take this 180 and go theta r is equal to 180 degrees minus 125 degrees. And then this is going to be equal to, well, if we did, let's say, 180 minus 30, this is going to give us 50. And then if we add another 5 to that, this is going to end up giving us 55 degrees. Awesome. So that's our reference angle. And again, we always write it in terms of a positive. So even though it's rotating negative, if you want to just calculate it using positive values, totally fine. All right. And in fact, I would actually encourage that. All right. If we go to negative 70, not negative 170, but just negative 70, we start on the positive x-axis, like always, no matter if it's a positive or a negative. Negative 70 is located in this quadrant 4 here, down here, and we're going to rotate this and be like, well, here is the angle rotation. This is 70 degrees, and more importantly, it's negative 70 degrees. But here's the interesting thing about this. If I rotate down from the positive x-axis to now in quadrant 4, well, remember by definition that our reference angle is actually the angle that is contained between the terminal arm and the x-axis, meaning it is this angle. We just need to make it positive. So we're going to say right below this, theta r, or the reference angle, is equal to 70 degrees because it still wants to be the same measure. It's still going to be 70. It just has to be positive, and then we're satisfied with this here. Awesome. All right, now let's look at a more like open-ended type of problem, like the one that we're going to give you here, where it says list all the angles theta. And when we say theta, we're referring to this symbol here that kind of looks like a 0 with a line through the middle. It's for an unknown angle, so list all angles that have a reference of 45 in the domain of 0 to 360. So that means for all positive angles, what is the different angles that are the angles in standard position with that specific reference. Now, here's how I would do this. If we say it's between 0 and 360, right away you want to draw out a Cartesian plane. So here's my Cartesian plane. We know we have we have our rotational angle here. We always are going to start on the positive x-axis, but I'm going to use some different colors to represent how this thing rotates around. Now, let's do this here just to label it. We have 0, we have 360, right? So if I return back to that same spot doing a full circle, I'll get 360. If I'm up here, I get 90. If I'm over here, I get 180. There we go. And then down here, I end up getting 270. Awesome. Okay, now we're going to label all the different regions in which there is a reference angle of 45. So the first one, we want to talk about when it's in quadrant 1. This is going to be where we rotate by 45 degrees. So I'm just going to zoom back in here and then write, hey, we've rotated 45 degrees. Therefore, one of the angles in standard position actually is 45, because if we're in quadrant 1, which is right here, then we always say it's between the terminal arm and the positive x-axis. So one of our solutions here, or one of the thetas, is actually just going to be equal to 45 degrees. There we go, comma, because we want to put the rest here. We're going between 0 and 360, where we rotate to all the positive angles, or all the positive terminal arms throughout the quadrants here. We're going to go over to quadrant number 2, put our arrow on the end, and then what we're going to do is we're going to rotate this way and be like, okay, if I rotate to get this angle here, well, again, we know that the reference angle that is tucked in here between the terminal arm and the positive x-axis or sorry, between the x-axis and the terminal arm, not the positive x-axis, but we look at it between the x-axis and the terminal arm is 45. How far did we have to rotate? Well, in order to get this angle here, what we had to do is we're going to take this and be like 180, which is a full rotation from 0 and across, so over to the other side here, or to the left-hand side, minus the 45. This is going to end up giving us that we have an angle of the following. Well, if I take 180 and minus 40, I get 140. If I subtract another 5, this is 135. So the angle that we actually make here in standard position is 135. And maybe what we'll do is we'll just like arrow down to this like this and just say that it is in that region there. So I'm just going to be like, from our positive x-axis rotating over, we end up getting 135. And let's just take this a little bit lower. I'm always a big stickler for making sure the information is organized. So I'm just going to lower it a little bit so that it is clearly in that quadrant there. All right, and then just one last label here for this quadrant. We want to say if that was quadrant 1, then this is quadrant 2 up in the top left. Now we're going to go down to quadrant 3 and see if we can solve for whatever this angle is. I'm going to use a different color. So again, I'm going to draw my terminal arm in quadrant 3. I'm going to show the rotation going in the counterclockwise direction just to show that it is a positive angle going this way. And then we want to be like, well, if we know that the reference angle, which is here, is 45 degrees, because it's always between the terminal arm and the positive x-axis, not the positive. I keep saying that in terms of, I keep thinking about the initial arm. We want to treat it as it's the terminal arm to wherever the closest x-axis is. Now, in order to solve this, we're just going to take the 180, which is currently there. So if I rotated using the orange to this point, at least, we have 180 degrees along the flat, but we want to add this 45, which represents the reference angle. So 180 plus 45. This is going to end up giving us that this angle is 225 degrees. Awesome. And this is symbolic of the angle that is located in orange here. And I know that it can somewhat get a little bit confusing when we put in all these arrows and all these things going around, and it's kind of hard to see, but hopefully this is okay. Now what we're going to do is we're going to go down to our quadrant 4 or IV, and we're going to put another color here. So let's say I use green. Why not? So I'm going to put my terminal arm here. I'm going to then say, well, my terminal arm and the x-axis or the nearest x-axis make my reference angle. So this will become 45. And then in order to solve for what this angle is, as it rotates from the positive x-axis all the way around, or it goes from here as the initial arm all the way around, we just take 360 and minus 45, and that will give us a solution for this. So let's do that here. I'm going to just move this IV a little bit if possible, and we're going to write this as 360 minus the 45. And this will give us some sort of degree. In this situation, 360 minus 45. 360, you start by subtracting the 40. That gives you 320 minus another 5. This gives you 315 degrees. And then we'll just make sure we put our quadrant label of IV right below that, and we're satisfied with this. And again, we could point to this angle if we really wanted to, but I almost feel like if we're pointing to this stuff, it's going to get a little confusing of like, okay, where are we rotating to and where are we rotating from? But hopefully this is decently straightforward here. Now, of course, we want to summarize all these solutions. We've started by writing out 45, but we also had 135. So we're going to write that out here. So 135 is the other solution. We also had 225. And then our very last solution was the 315. There we go. And I'm just going to make sure I kind of pull this down to organize it and highlight it, because this is all of the solutions that are contained within that domain. When they say domain, this is all the possible angles that would make this true, or all the possible angles that would have this reference angle of 45. Awesome. Okay, now let's shuffle our page here, and we're going to look on the summary of how do we calculate angles, and then how do we calculate reference angles, and let's just provide a quick sketch for each of these. So let's say we're in quadrant 1. Well, the value of the angle theta is just theta, so we look at this one and we're like, theta can be between the following. It starts at 0, and then as long as it's between 0 and 90, we consider this to be in quadrant 1. And then if we go to quadrant 2, we consider this to be between 90 and 180. If we go to quadrant 3, this is between 180, and I'll make that less than a little bit better. There we go. And 270, because that is our quadrant 3 endpoint. And then in terms of the last quadrant, it's all the values of 270 degrees and then contained within 360. Awesome. Perfect. Okay, so this provides us a bit of a template in terms of like what values would we expect in these quadrants. But now we want to figure out what the reference angle is. The nice thing about quadrant 1 is actually whatever the angle is the reference angle. So it's pretty easy actually. We just say theta r is equal to theta, and as soon as you know that angle, you're good. And here's the reason why. If we provide a rough sketch here, if I start on the positive x-axis, which means here is my initial arm, my terminal arm is here, it means the theta r is always the angle that you created using the initial and the terminal arm. All right, now, what does that mean? Well, when we go over here, we could say that, hey, you know what? The value of the angle would always equal to the reference angle. We could throw that below if we really wanted to. I mean, I don't really see a need to, though, in this situation. All right, let's go to our next quadrant. Quadrant 2, if we're in quadrant 2 and it's between 90 and 180, in order to get the reference angle, you're just going to take 180 and minus whatever the angle is. So we're going to say theta r is equal to 180, which is a full kind of half, I wouldn't want to call it a full rotation, but it's a half rotation minus whatever the angle in standard position is. And if you minus the angle in standard position, you end up getting the reference angle. And just to show you this is how it works, we're going to write our Cartesian quadrant. We're going to start on our positive x-axis, just like we've done all the times before. We're going to put some sort of terminal arm in quadrant 2. And then when we look at this, we're like, okay, we know that the angle in standard position is this one here. So I'll write that as theta. This one is theta r. And then our endpoint we know is 180. This is 0. And so maybe I'll include that on the diagram up above too, 0 here. If we take this, then we're like, okay, 180 minus whatever our angle in standard position is will give us the little sliver that is between the terminal arm and the x-axis. Awesome. Okay, now we go down to 180 and 270. To solve this one, we're just going to take the theta r and set it equal to the angle in standard position minus 180. Now, the reason we can do this, and we're going to show it off on our graph here, if I write this below, I can be like, well, I always know that I'm going to start on the positive x-axis. That always happens no matter what. And then we list this as 0 degrees, right? So that's our start. When we're in quadrant 3, this means our terminal arm is going to be like this. We rotate it around, so we're like this, going counterclockwise. In this situation, that represents our theta, which is our angle in standard position. And the little sliver that's existing between the terminal arm and the nearest x-axis is the reference angle. This is 180. And so if we know that that represents some total angle and the 180 represents the kind of endpoint in which we can subtract, then we're going to get this little sliver that's between the two, between this angle that rotates all the way around and 180. If we subtract those two, you get just that little sliver remaining. Okay, lastly, we go into quadrant 4. The way we summarize this one is we say, well, the reference angle, in order to solve this, we're just going to take a full circle, which is 360, and then just subtract away the angle in standard position. And visually, this is what it would look like. If I have my Cartesian plane roughly sketched, here it is. I would start with my initial arm on the positive x-axis. I would rotate to where I'm in quadrant 4, which is down here. We know that between the terminal arm and the x-axis, we say that this is considered to be the reference angle. In order to get this angle, I had to rotate counterclockwise all the way around here by some amount of theta or some angle in standard position. And then if we look at this just using our measures here, we started at 0, we rotated past 180, we got all the way over to where it's nearing 360, not quite at 360. So the way we're going to solve this is take 360 and then minus what we would have rotated in order to get to that point, because a full circle minus the little sliver that we've generated, or not the little sliver, I guess it's in quadrant 4, the bigger sliver, this is going to leave us with just this small piece that sits between 360 and wherever the angle rotated to. All right, so there's our generalized form. Now, let's continue to work with this in example 3. Determine the angle in standard position when the angle of 50 is reflected in the y-axis, aka about the y-axis, just like we did in our quadratic functions unit, in the x-axis, and then in the y and the x-axis, which just means a reflection in both. So let's start off with the first one here, and we're going to say, okay, I always want to start with my initial arm on the positive x-axis. I'm going to draw in my 50 degrees here, which is going to be the following. I have some sort of angle of 50 degrees in quadrant number 1, like this, because that's where an angle of 50 degrees would lie. And they say reflected in the y-axis, that means this is what's going to happen with it. I'm going to then reflect it this way, because technically I would take that same line. I should almost mirror it exactly to the T. There it is. So that means that this over here is going to be 50 degrees, because by symmetry, we know that that piece is 50. It's reflected over the y-axis, or it's reflected this way. And now we want to figure out what that total degree is. The total degree of this in standard position is going to be that full rotation from the positive x-axis over to our terminal arm. So I'm going to write a theta just right above that. In order to get this, what we're going to do is we're going to take 180 and subtract 50. And so I'm going to go like this just below here. If I want to end up solving this, where this is 0, this is 180, then in order to get this angle in standard position, theta is equal to 180 minus the reference angle here, which is 50. That's going to end up giving us the theta, which is equal to 130 degrees. Awesome. So there's our solution here. So if it's purely reflected across the y-axis or about the x-axis or in the x-axis as they call it, we see it as a reflection over the vertical line. Now what we're going to do is we're going to look at this and say, well, instead, let's take that same 50. So let's take a quick sketch here. I'm going to draw my positive x-axis, aka my initial arm. I'm then going to draw the angle in the first quadrant because that's going to be our 50. We're going to write this as 50 in here. And instead of reflecting about the y-axis, now we reflected about the x-axis, which means it gets reflected vertically like this instead of horizontally across the y-axis. And now what I'm going to do is write this below and be like, well, if it was 50 above, it's 50 below. Whoops, my apologies. Don't want to have text we can't read. 50 degrees. Now, to get this angle, I start on the positive x-axis, rotate all the way around. This ends up giving me a theta. In order to solve for that red theta, I need to be like, well, if this is 0, this is 360, which is a full circle. In order to solve for that angle in red, I'm going to look at this and be like, well, theta is equal to a full rotation around the circle minus the 50 degrees, which represents the reference angle. And if I subtract away that 50, which is that little slice, 360 minus 50, this ends up giving us 310 degrees, which is the solution here. Awesome. Okay, now let's say I want to do both reflections. So I first want to reflect across y, and then I want to reflect across x. Well, let's actually draw that out in sequence. I'm going to start off by doing the same thing I've done. We're going to put a line across the positive x-axis, representing that this is our initial arm. We're then going to say, okay, well, in quadrant 1, this created the 50 degrees. So let's make sure I have the appropriate tool here, 50 degrees. We're going to do our first reflection across the y-axis, or this kind of horizontal reflection, if you want to call it that, across the y-axis. That means that this is going to be 50 down here. Perfect. And then in green, what we're going to do is do the next reflection. I then reflect about the x-axis. I've done the y, which put me over to quadrant 2. I will then do the x reflection, or the vertical reflection, over the x-axis, or about the x-axis, if you want to call it that, which will again give me 50 in terms of the reference angle. And then from here, I just want to trace this and be like, hey, maybe I represent this in steps. So from here to here, this was going to be step number 1. There we go. And then from here to here, this is step number 2. Perfect. Okay. Now, what we're going to do is from here, we want to figure out this total rotation. The total rotation, I'm just going to have on the inside like this and rotate all the way around with an arrow. I'm going to put a theta above it. In order to solve this, we know that we can take 180, which is, because if we started at 0, we did our original reflection, which put us over to 180, which I know is a little crammed. And then we ended up adding another 50 to get to that green line. Then whatever this theta is, in this situation, the angle is equal to 180, which is at least how much we have, plus the reference angle of 50. This ends up giving us theta is equal to 230 degrees. So that's where this arm will terminate in green. And we want to make sure we highlight that and we feel perfect with that solution. Perfect. Now I'm just going to make sure that's just a little neater. There we go. Awesome. Okay. Now, when we go on to one of our last pages here, if not, I believe it is our last page, it is. So what we're going to do is in this example here, they say determine the angle in standard position given by the point 4,3 that lies on that has this point that is on the terminal arm. So when they say this, what you want to do is you want to go over to your grid and you want to go to 4,3, 4,3, which would put us right here. The line is going to cut through this and start at the origin. So this is where it terminates. There we go. And what we can do is we can just put like a little arrow on the end if we really wanted to. We can put our initial arm down here, which is like this. So it's going to be over by the 4 units like this. Perfect. Now what we want to do is we want to break this apart. If we know that the x is going to be 4, we're going to label it. So we're going to put 4 right below here. If we know that it has to go up in order to get to that point, from the initial arm to the terminal arm, it has to raise up by 3 vertical units. We're going to make sure we put that there. And then we're looking for this angle that's on the interior here, or whatever this angle represents. So in this situation, we want to set this up using some Math 10C knowledge and be like, okay, well, if I have an angle and I have the opposite over the adjacent, that means I'm using the tangent ratio, and I'm going to go tan of theta is equal to this ratio of we go the opposite over the adjacent, or 3 over 4. In order to get my theta alone, remember we always invert that function, so we're going to go tan inverse of 3 divided by 4. And then therefore, we're going to end up getting theta is equal to, well, we want to pull this up in our calculator. In fact, I'll probably just do this off screen just to pull this up here. I'll make sure we're in degree mode. That's super important for this unit. I will make sure I mention that throughout the unit as well. If I go second tan and I take this fraction of 3 over 4, it will give me roughly to the nearest degree. Did they say anything about to a specific degree? Let's just round it to the nearest whole degree. This will be 37 degrees. Awesome. So when we have a point and the terminal arm cuts through that, we end up getting this 37 degrees. Now, suppose that we took this same thing and we reflected it in the x-axis to the new given point. Well, what would that mean? We would be in the situation of reflecting below the x-axis, which would actually put us somewhere in quadrant 4 here. And we would be down below because when we reflect about the x-axis, it's actually a vertical reflection. And so we would have this where it's 3 and 4 still in the same position. If we solve for the angle, it would be the exact same thing, but we could look at this and be like, okay, well, maybe I'll actually just do this in, let's say red. I'm going to go down to where it's at 4 and then -3, which reflects it to here. And then I'm just going to draw a dotted sequence of lines through this. There we go. So dot, 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 and then dot, dot, dot. This is also 3 down here. So we're going to write this as 3. This point on the end right here, we're going to label it as the following. This is at 4 and -3 when we reflect it. So that's the point we're going to record here. We're going to write that this occurs at 4 and -3. And then what is that angle here? Well, that angle would be the following. If we talk about that full angle of how it rotates over to that quadrant, it must be starting at the positive x-axis here and then rotating all the way around to the red line, meaning we can take 360 and -37 and get some sort of angle. So I'm going to write this as theta is equal to 360 and then minus the 37. Well, if we take 360 and -30, we get 330 minus another 7, and we end up getting 323. So this is going to be equal to 323 degrees, aka that's where it lies in quadrant 4. Now, reflect the angle in the y-axis and given the new point. Well, in this situation, if we reflect it and get that new angle, I'm going to show this in green. We're going to end up going over the y-axis and going to -4 and +3. That means our angle terminates right at this line here. And if it terminates at this line, then when we create our triangle here in green, which will look like this and this, we're going to have this at -4 and +3 up. So the point that I'm going to put at the end here is going to be -4 and +3. If I was to calculate this in terms of how far this is rotated over to terminate at this specific spot, we would say that if the point is at -4 and +3, then the theta can be calculated by taking 180 and subtracting this 37. So 180 minus 37. Well, first of all, take 180 minus 30 gives you 50, minus another 7 gives you 143. So the angle in that quadrant 2 would be 143. Okay. And again, when I say these angles, what I refer to is it always starts on the positive x-axis as the initial arm, and it rotates over to where it terminates or where it crosses through that point. Okay, now reflect the angle in the y-axis and then the x-axis to give the new point. Here's what it's going to look like. Just like we did before, I'm going to maybe choose a different color here. So let's say I choose, I'm going to choose orange. Now, if I go down below here, it's going to be at -4 and -3. The line or the terminal arm would locate on this orange here. And to get there, we have to go by -4 units, but we have to go down by 3 units. And so when we look at this in terms of a ratio that we would use here, well, that's going to be a 3/4 when you take care of the positives and negatives. And so we want to just list the point out, of course, just like they're asking for. It's at -4 and -3. And then for the theta, we're going to say that it is the angle in which it gets to, which in this situation, we don't know that angle, but we do know the reference angle. The reference angle in all of these cases, or these little angles that are contained in here, are all 37, which we've already solved for. So we're going to take 180 and add 37. So 180 plus 37 degrees. This is going to be equal to 180 plus 30 is 210, plus another 7 is 217 degrees. Awesome. Okay, now what can you say about the reference angle of each of them above? Well, exactly what we just stated. The reference angle for all of these, or the angle that's embedded between their terminal arms, which are all the ones I'm going to indicate in red here, and the x-axis, which is right here, they all have 37 degrees nested where I've just drawn those circles. Okay, so I'm going to just make a note about this. They all have reference angles, which I'm going to call theta r, of 37 degrees. Perfect. All right, we got one more example here, and it's dealing with what happens if we take a point, and this point is on the terminal arm when it rotates, and it's in quadrant 1. State the coordinates of Q, R, and S given that the terminal arms terminate in quadrant 2, 3, and 4 for Q, R, and S respectively. Now that probably sounds like a mouthful, but let's just deal with this here. I want you to draw a basic Cartesian plane like this, and then I want you to just draw that point somewhere in quadrant 1, whatever they've told us it is. So in this situation, I'm going to be like, here's the point, and then I'm going to just draw from the origin over to that point. There it is. Now, this point, let's make sure we write this in here, is indicated by P, which is located at 3/2 and 1/2. And if you're like, what the heck is this? Like now we're just dealing with like P's in terms of we have like some sort of radical and fractions. These are what we call exact values. And we're going to get into this very, very soon. So don't worry. Just know that it's representative of some sort of X and Y pair that represent some sort of relationship in the Cartesian plane as a point. And then we'll get more into how this relates to sine, cos, and tan in terms of exact values. Don't worry about it too much for now. So here's all you need to know about this. When I start playing around with these values, all I'm going to do is when I move it into the different quadrants, if this is quadrant number 1, so maybe what we'll do is we'll write all the numbers just right up in the, kind of right near the axis points here. So there's 1, 2, here is, maybe I'll write 3 below here. So here is 3, and then here is 4. When we have these all as 1, 2, 3, 4, and I start rotating them all around, to get to Q, we know we're going to go to quadrant 2. So what I'm going to do is I'm just going to draw a point that is approximately at the exact same position, just over in quadrant 2. What does this mean I do in terms of my values? The Q is actually going to be the following. Q is equal to, we take this and we're like, well, if X was positive 3/2, on the left-hand side of the X-axis, this is where it is negative. So it's going to be negative, whoops, there we go, negative √3/2 and positive 1/2, because the y values in this quadrant are still positive. It's just the x values that become negative. Now, similarly, I'm going to put a point down below into quadrant 3. Let's say it's about here, because we want to make sure that it's roughly about this similar, kind of similar distance and direction. So we may even want to shorten p, but just to be lazy, maybe we don't. I'm going to now look at this and be like, well, the point now alters to be the following. If this is point R, Well, down in quadrant 3 here, what happens is that the x and y both become negative, so r actually follows the following form. It's going to be negative root 3 over 2 and negative 1 half, because we're not only a negative x value, we're also a negative y. Lastly, in green, what I'm going to do is do the fourth quadrant. So let's say that this is point S. Point S starts at the origin and then ends up at that point, because this is the terminal arm that crosses through that point. What changes? Well, for point S, as we're going to call it, what we have is we have a positive x value because it's on the right-hand side of the origin. So this becomes root 3 over 2, just like it was in the original, but now it's the y value that becomes negative. And so we want to write it in the following form. So these are all the points, P, Q, R, and S, such that we've adapted them so that the X value is the appropriate in terms of being negative or positive, and the Y values are either positive or negative respectively. And again, here's how you can summarize it. All the positive Y values are above the X axis, so it was positive and positive. All the negative X values are on the left-hand side of the X, or on the Y axis. So we saw negative X and negative X. When we saw the negative y's, it was when we had them below the x-axis, so it was negative a half and then negative a half. And then the last thing is where they're both positive is always going to be in quadrant 1. All right, what I'm going to do is I'm just going to shift this over because that actually answered all our questions in terms of labeling this correctly. I'm just going to shift it right to here, and then we'll call that a lesson. Now, here's where you're going to want to go into practice dealing with initial arm, terminal arm, reference angles, how to find them, because it does take a little bit of practice and you'll want to get this or pick this up. All right, good luck with your practice.